Well, welcome to the AASHTO Technology Transfer Fair. It's being held here in Milwaukee in conjunction with the 1991 AASHTO annual meeting. SHRP has a large exhibit here of about 50 of the 100 products that were being developed within the SHRP program. And the theme of our exhibit is SHRP Now, because now is the time for states who have paid for this program to begin to implement many of the things that are coming out. Throughout the exhibit, we have a number of the different technologies that have either have been developed through the SHRP program or which are being used as part of SHRP's data collection effort. SHRP, of course, was begun back in 1987 as part of the highway bill in that year, and the states, through that legislation, decided to spend $150 million in this intensive 5-year research program to address some of the major problems that they're facing in asphalt, pavement performance of concrete, and the maintenance of our roads. I hope that some of the exhibits that you see here as we give you a quick tour of this exhibition will give you some idea of what's now starting to come out of this program. Now is the time to get interested in SHRP. The things that you've been paying for to develop in this program are now available for state use, and I hope you see something in this exhibit that will allow you to do a better job in your state. Thanks. Let's start our tour by looking at some worker safety devices. Hardly a week goes by without a maintenance worker getting killed by traffic. There are a lot of devices to make maintenance work safer. We'll show you a few.
My name is Dale Stout. I'm with ENSCO Incorporated, a SHRP contractor. The job we are working on is entitled Maintenance Work Zone Safety Devices Development and Evaluation. The first device is a queue-length detector. How would you would use it? You would place it at the end of your desired traffic queue. When the vehicle is sensed by the ultrasonic device, it alarms the flagger. The flagger then knows to release traffic so that a queue does not back up into an intersection or over a hill. These two devices are maintenance work zone safety devices, worker warning devices. The first is ultrasonic. You would place it inside your taper, past the end of, within 500 feet of your work zone. When a vehicle passes through the taper, passes through the ultrasonic beam, it would alarm the horn in the work zone, alerting the workers to head for the shoulder because a vehicle has penetrated into the taper. The second device is an infrared. It works on the same principle, except it needs a beam to bounce back from the cone. And when the beam is broken, it again alarms the workers. This is a flashing stop-slow paddle. The feature of it is the flashing lights. This increases the visibility and makes people slow down much more quickly when entering the work zone. The next device is a direction indicator barricade. It is similar to a standard A-frame type barricade, except it gives the visual clue with the arrow of which way the traffic should head. This device is a portable speed bump. You would place this upstream of your flagger or your work zone, and it acts just like any other speed bump or rumble strips. It makes the traffic slow down. This device is a direction indicator barricade. You would place it in a situation where you have a 4-lane two-way traffic merged into a 2-lane two-way traffic. It gives the additional visual clue to remind drivers that they are traveling on a two-way, 2-lane zone. The large sign is a portable sign stand. It allows for placement on uneven terrain, such as cuts and fills. The stand is placed, spikes are driven in the ground to hold it in place, and then the center portion is rotated to allow the sign to remain vertical. This device is named the diverging lights. The lights flash from the middle 2 bulbs to the second set of bulbs to the third larger bulbs. It's designed to actually trick the driver into think he's closing on something more rapidly than he is and apply the brakes to slow down. These are snowplow blade marker delineation lights. They assist the drivers passing a snowplow in determining at the edge of the snowplow location so as they don't impact the snowplow when coming back into the lane due to the snow cloud. They also inform the driver of the snowplow as to the edge of his snowplow so he doesn't cut through lanes or cut off through the guardrail.
I'm Glenn Berkman with the Minnesota Department of Transportation. Behind me I have a remote-controlled shadow vehicle. These are the controls for controlling the unit. It's used for work zone safety, to protect the workers in the work zone and the driver of the vehicle. The unit is worn around your neck. It has a dead man switch. It has a forward throttle, braking. We have a transmission for forward, neutral, and reverse. We have a steering selector for left and right, four-way flashers, lights, and directional control. The operating distance is 800 feet. Top speed is approximately 5 miles per hour.
Let's look at some new solutions to the age-old problem of keeping the roads open in winter. I'd like to show you some improved snowplows, new weather information systems, and an attenuator that you can use with a salt spreader.
I'm Don Harriet with SHRP. The experimental snowplow that has been developed has a flexible mold board made from high-density polyethylene. This flexible mold board allows the researchers to experiment with different shapes of the snowplow mold board to get an optimum shape for different kinds of plowing activities. Either high cast for casting snow over a median barrier, or for long cast to get the snow as far away from the roadway as possible. By changing the turnbuckles at the either end of the snowplow to change the shape of the moldboard, the researchers were able to experiment with these different shapes. There's another point on the snowplow I'd like to explain, and it is the snow scoop that is at the bottom near the cutting edge. This front nylon snow scoop blade allows the snowplow to get under the snow on the highway so that the snow is swept gently over the snow scoop up into the moldboard so that it can then travel out along the moldboard and be pushed off the highway. Underneath and behind the nylon snow scoop is the conventional carbide steel cutting edge, which takes off the ice and hard snowpack on the pavement. This snow scoop and combination snow scoop and the carbide cutting edge is a new SHRP development, and the snow scoop reduces the amount of energy required as the plow is pushed through the snow. It also reduces significantly the amount of side thrust that occurs from the angle of the plow as the truck tries to push the plow through the snow. So it is a much easier and safer plow to operate for the operator because of the reduction in side thrust.
What you see here is our 2001 MD truck-mounted attenuator. Along with this particular system, we have a salt spreading attachment that can go on that will allow you to spread salt and have protection. We find a large number of hits have occurred in the wintertime under whiteout conditions where you might be plowing at 20 or 30 miles an hour and the impacting vehicles is going slightly faster. They don't see you and run into the back of your vehicle and tear up your equipment and cause a potential problem for the impacting driver and the state driver. So this will allow you to have TMA protection while you're spreading salt.
I am Elmar Reiter of Wells Research Corporation in Boulder, Colorado. We are under a contract with the SHRP IDEA program to develop a weather prediction system that is portable and very user-friendly and will provide very localized predictions for highway maintenance. Here is, for instance, an example of a condition. This happens to be a winter blizzard that came up in the Denver area and absolutely closed down Denver with 3 feet of snow. But in addition to this kind of prediction, we are able to bring up not weather maps, but bring up maps of a foreman's area or a highway maintenance district area and display weather information in a very user-friendly way by just painting, for instance, the topography in colors that you can interpret as depth of snow. And furthermore, the user will be able to integrate information into that forecast and upgrade the forecast. For instance, if we forecast for you 5 inches of snow and you get the call from a highway patrolman and says, my gosh, you guys, I'm standing up to my knees in snow, we can point and click at the map and it will automatically upgrade the weather forecast. So with this kind of a facility, we will be able to provide you with a much better handle on targeting and scheduling your resources. Our aim is to shave your winter maintenance budget by 5%, and that 5% you can use for much better things than shoveling snow when it isn't there.
Need to save money in your maintenance operations? Learn how to evaluate maintenance materials to determine which are the most cost-effective for your needs. Or in a few years, you may want to consider new maintenance equipment, like a crack-filling robot that we're still developing.
So this is a pavement crack-filling robot, and the idea behind it is to reduce the number of workers out on the roadway filling in cracks and reduce their exposure to traffic, and also try to improve the consistency of filling in the cracks. The effort, or the research effort on this project, was to concentrate on reliably detecting cracks for the cleaning and filling operation. The way we do this is a combination of video and range data. The video camera takes a picture of the blacktop, and the problem with just using a straight picture of the blacktop is that discolorations on the blacktop appear also to look like cracks. So in order to corroborate cracks that are really there and dismiss the phantom cracks, we use a infrared range sensor to determine the depth. And by detecting a change in the depth of the pavement, we can corroborate a crack that's really there and dismiss a crack that's not there, that's due to, say, discoloration in the pavement. With that information, we can plan a path for the robot to traverse, first to blow the crack out and then to fill it. And then you see down there, there's two effectors, one for the blowing operation and then the second one for the filling operation.
My name is Mark Baker. I'm with the University of Texas at El Paso, and here we have the prototype of a non-destructive testing device using acoustic wave propagation. This is designed to detect the precursors to distress that may occur in the pavement. It relies on acoustic wave propagation from acoustic hammers through a series of accelerometers and geophones. It's designed to be operated by a maintenance technician after about 1 week of training. We use air controls to lower the transducer mounting bar to the pavement surface. The hammers, both a low frequency and a high frequency hammer, are used to generate waves that propagate through the arrays.
My name is Brian Cox. I'm on loan to SHRP from the Transport and Road Research Laboratory of the United Kingdom, working in the highway operations area, and I'm going to talk to you about this pothole patching experiment where a number of materials for repairing asphalt pavements and for repairing concrete pavements are being used throughout the United States in the various states to repair potholes in various conditions and using various methods. Hopefully out of this we will know what works best for longer lasting pothole repairs.
Better quality concrete means better quality roads. We'd like to show you some new ways to prevent costly damage from freeze-thaw or alkali-silica reactivity. We've also developed some new non-destructive test devices for assessment of in-place concrete, both for permeability and for chloride damage, and for testing the effectiveness of bridge deck sealers.
What we've done here is developed a piece of apparatus for determining the permeability of concrete surfaces. And this is important because steel reinforcement in concrete bridge decks and support elements can be corroded by de-icing salts which seep into the concrete. The more permeable the concrete, the more salt will get in, and the sooner the steel will start to corrode. What we've done is develop a method for drawing air through a surface of concrete under a vacuum. This gives us an indication of the permeability of the particular concrete, and we find that this also is very indicative of the rate at which de-icing salts will enter the concrete, as well as other substances such as water. This is the device. This is a battery-powered device that can be used in the field, and I'm going to demonstrate it now. In order to effect a good seal to the concrete, we place a foam rubber gasket on the spot we'd like to measure. We place the device on the gasket and then stand on it in order to effect a tight seal. The vacuum pump is then turned on, the device is powered, and vacuum is applied to the surface. Within 1 minute of applying the vacuum, we're able to take a reading which is an indicator of the permeability of the concrete. I have two slabs of concrete here. One was produced with a very high water content, and this will make the concrete very permeable. The other was produced with an admixture termed silica fume, very finely divided form of silica, which blocks the pore system of concrete and creates a very dense, impermeable material. Our permeability scale runs from 0, which would be essentially impermeable, on the way up to the capacity of the meter, which is approximately 100 cubic centimeters per minute. This concrete reads 30 cubic centimeters per minute, which is a very high value. This shows the flow reading in cubic centimeters per minute, and this is the vacuum level. We operate at a vacuum of from about 620 to 640 millimeters of mercury. This is the elapsed time of test. We're now testing the silica fume concrete. As you see, the flow level is down to 2 cubic centimeters per minute. This is a very low level. Anything below 5 is indicative of very dense, impermeable concrete, and this is fairly close to 0, indicating a very dense and impermeable surface.
Hello, I'm Bill Ost. I'm with CTL. We developed this simple test method for evaluating in the field the effectiveness of penetrating sealers. Very briefly, the way we do it is we use a conductive silver paint, and we paint through this mask to produce a gauge with a fixed geometry that has 2 stripes of conductive paint and a center stripe that isn't painted. And if we then wet this with water for about 5 minutes, and at the end of that time we wipe off the excess water with a towel, and if we measure the AC resistance at about 4 minutes, by the resistance reading we can then tell whether the coating is ineffective, is of average effectiveness, or is highly effective. This inexpensive method would be usable for quality control during the application of a sealer, or for determining the maintenance required.
My name is Anthony Alonji from Penetradar Corporation. This project here involves the use of radar, ground penetrating radar, for the lamination detection in bridge decks. The equipment we're showing back here is a ground penetrating radar system, similar to conventional radar in many ways, except for the fact that it's looking down instead of looking up. Instead of looking into free space, we're looking into solid materials such as asphalt and concrete. And our use here is for asphalt-covered bridges. This equipment I'm showing here consists of a transmitter-receiver unit, antenna. The equipment installed in the rack consists of a radar control unit, computer interface unit, which controls the data flow between computer, display, and computer monitor. What we're showing on the screen is a typical radar waveform from a bridge deck. And basically the radar is operating in a manner similar to acoustic techniques. However, we're operating at a much higher frequency, and the signals are microwave in nature. For bridge deck delamination, we found that the signal varies in accordance with the chloride and moisture content in the concrete. And accordingly, the signal will attenuate, and the reflectivity at the asphalt concrete boundary will vary relative to that. So what we look for bridge deck delamination is an increase in the asphalt concrete echo, as you're seeing there, and an attenuation caused by the increased conductivity in the concrete subsequent to that. So based on those discriminants or indicators, the computer performs a detection and detects the delamination in that manner.
I'm Don Jansen from University of Washington, and I'm the principal investigator for SHRP contract C203, resistance of concrete to freezing and thawing. One of the problems we have with freezing and thawing in concrete is we make a perfectly good mix, make it correctly, get the correct amount of air in it, but if we use the wrong aggregate source, the material will be non-durable. You make the concrete up, and after about 5 to 10 years, you start seeing cracking like this, and the material is just totally deteriorated at the joint. So what we'd like to do is to avoid that. The standard way to avoid that is to test each aggregate source before you use it. The standard test method is to make concrete beams, cure them for 2 weeks, and then do a freeze-thaw test on the beams. That freeze-thaw test takes anywhere from 6 to 8 weeks. So potentially 10 weeks after a contractor submitted an aggregate source, you tell them that the source is not going to work, he has to submit another source. That's a little bit of a problem to a normal construction schedule. What we did in the SHRP freeze-thaw project was to develop a more rapid test. Instead of making concrete beams, we take the aggregate piece and surround the aggregate with water. It starts out oven dry, surround it with water, and we pressurize it to 1150 psi pressure. This forces water into the pores, compresses the air in the pores, so we have pressure on the outside, pressure on the inside. We then rapidly release this outside pressure. The pressure on the inside wants to get out. If we've got a very coarse pore system, the pressure gets out very easily. Those aggregates don't cause problems. If we have a very fine pore structure, the pressure can't get out and the rock cracks, and we get the little pieces. And that is what this mechanism here does. The aggregate is inside of here, it's full of water, and it's hooked up ready to pressurize. Pressurized up to 1150 psi. In our normal testing procedure, we would hold the pressure on for 5 minutes, and then we would release the pressure. It's pressurized. To release the pressure, it's very quickly, a little bit loud. And the pressure is relieved. The pressure on the inside of the aggregate, as I mentioned, has got to dissipate, and that'll happen. If it can get out easy, the rock doesn't crack. If it can't get out easy, the rock cracks, sometimes in half, sometimes little pieces come off. And what we do is count the number of pieces we had before, count the number of pieces afterwards, and what we get is the percentage of increase in pieces or the percentage of fracturing. We normally do 10 cycles of pressure in 1 day. It takes about 45 minutes to an hour to put the sample inside, bolt it up, and get 10 pressure cycles. We then oven dry the rock overnight. Next day, we count the particles. We do that for 5 days for a total of 50 cycles. A bad aggregate would probably have 10% or more fracturing at the end of the 50 cycles. A good aggregate would probably have 5% or less. So we can then tell the difference between good and bad aggregates by the percentage of fracturing. We've tested a little over 20 aggregates so far. We've got no false positives. That means that none of the aggregates that have passed our test have had any decracking problems in the field. We've had one false negative. An aggregate failed our test, but it was still a good aggregate. So this means we're not going to replace freeze-thaw testing, but based on our test, you could accept an aggregate for use after the total time is 8 days of testing. If you wanted to reject the aggregate, you would probably continue on and do the freeze-thaw testing, but in the meantime, you could tell the contractor that the aggregate will probably fail from freeze-thaw testing. He should find another source for testing at the same time, rather than waiting the full 10 weeks before the final result in that it has failed. So we've come up with a test that's fairly quick. The equipment is fairly inexpensive. We believe it should be able to be manufactured commercially for about $10,000. We built this by hand for around $7,000, and commercially they should be able to do that for less. So for $7,000 or $10,000 in 8 days, we can get the same kind of results that it would take you to get maybe 8 to 10 weeks to get a result from. So that's the test for identifying decracking aggregates.
My name is Inam Javed. I am the manager for concrete project at SHRP. And one of those projects is the alkali silica reactivity. As you would see from this brochure, this is a widespread problem in the United States. This is essentially a chemical reaction between the silica, certain forms of silica in the aggregate that is used in the concrete, and the sodium or potassium or alkalis that come out of the cement. The result is an expensive product which absorbs moisture and expands and finally leads to the destruction or disintegration of the concrete. One of the problems that we have, that this problem goes on unrecognized. And often the damage that you see to the concrete could be due to other factors other than the alkali silica reactivity, such as the freezing and thawing, corrosion of reinforcing steel. So this test that we have developed under SHRP will identify if that particular problem or damage to the concrete is due to this alkali silica reactivity. Now the test is very simple and doesn't require any expertise or any expensive equipment. All you do is take the concrete specimen, spray that with this uranyl acetate solution, put it in a dark background and look under the ultraviolet light. And if there is a reactivity, it will show up as a greenish yellow color. And the test from start to finish takes about 10 minutes. The equipment that we use costs about $250, and this is portable. You can take it to the field. You can do it right at the on the pavement or any structures, and so you don't have to make coats, you don't have to polish, and you don't need a petrographer to do the interpretation.
Joe Lamont, the SHRP staff. I'm going to tell you about a new procedure for removal of chlorides from a concrete bridge deck. I have here a model of a bridge deck, which is these little green dots are the chlorides that have been penetrated into the concrete. This new procedure involves damming up the deck and putting down a layer of mesh, tying this mesh to the reinforcing steel to get a circuit, and then flooding the deck with a electrolyte solution. After this is performed, we put a charge on the deck, and this charge removes over time the chlorides back into the electrolyte solution. It takes approximately 6 weeks until a great percentage of the chlorides have been removed. At this time, the system is complete and the deck is put back in operation.
My name is Mark Henry, and I'm here to demonstrate the new chloride extraction method developed at VPI. What we have here essentially is an impact hammer with a hollow bit. Bit itself has a center core that comes up to this ring where a vacuum is applied allowing you to extract the grinded concrete up at the interface of the bit. Concrete dust is then traveled through the tube into a collection unit, shown here, in which a coffee filter retains the material, allowing an operator to easily open and collect the sample, which can be installed into a simple polycon for evaluation there at the deck or in a laboratory situation. Here's essentially the equipment that we use for determining the chloride content of that powder. It contains simply a digestion solution, which is an acid-based solution, 20 milliliters of this, 3 grams of your sample that you just extracted will be added to this solution. 2 minutes is allotted, allowing the material to be digested adequately, breaking up all the cement, at which point 80 milliliters of distilled water is added into the solution. That's to dilute the solution for high concentrations and to eliminate the exothermic reaction that occurred. After about a half a minute to a minute interval there, this specific ion electrode is introduced into the solution. In doing so, the millivolt readings will change in accordance to the chloride content. High numbers on this will generally mean very low chloride contents. Low numbers are high chloride contents. These millivolt readings are written down after 2 minutes, in which time they're taken and put into a mathematical equation and to determine the actual chloride content. And all this has been correlated to the original AASHTO method for final analysis. What we have here is a corrosion rate meter, one of 5 that were looked at by SHRP. I'm going to generally go over the understanding of it. First thing it has to be done is what it does is it determines the corrosion rate of the steel in the concrete non-destructively. Your first connection has to be made to the reinforcement at some point, and that you do have continuity to your point of application. At which time the surface has to be completely saturated. The equipment is very sensitive to the moisture content and the surface condition, so pre-wetting is mandatory. Once your deck is sufficiently wet, this part of the unit is placed in line. Well, this line here represents the line in which the direction of the steel is placed, and centered over it. At this point, you now can go to the equipment itself. The equipment is very self-explanatory. It doesn't require a lot of know. It gives you the 2 options in the beginning of a measurement or a database. There is a lithium battery that allows you to retain all of your information after you've run your measurement. So at this point, we're going to run the measurement. The first question it asks you is the area of the steel, and that is the area of the diameter of the steel, and it is in metric units. The particular bar we have here is a number 4 bar with an area of 55.86. At this point, it'll now show you the corrosion rate, the potential of the reinforcement. Once it's stabilized, this OK symbol will show and tell you that you're allowed to continue with the test. First part is phase 1. There's essentially 3 phases. Phase 1 starts the initial polarization of the steel. Phase 2 enacts the outer ring, since this is a ring guard system. And the third phase is a simple balancing, allowing you to make sure that your calculations were correct. This takes approximately 5 to 8 minutes, depending on the corrosion of the steel. Upon the completion of phase 3, the corrosion rate is displayed. In this case, it was 0.650 microamps per centimeter squared. After the test is concluded, you're given the option to store it or exit it. Before I store it, the equipment does retain this information. It retains the potential that you started with, the resistance of the concrete, the area of steel that you put in, the polarization time, and also corrosion rate. Now to store the all your data, you simply give it a reference point, give it 0.1, and your operator code. Again, we'll enter 1. You're measuring date so that you do not forget when you took your measurements. And that completes the test.
We can make asphalt that lasts longer and doesn't cost more by using new tests to select materials and design mixes. Let's take a look at some of this new laboratory equipment and at a computer program that will make it easy for you to use it and to build high-performance asphalt pavements.
This equipment is called the Universal Test System. It was designed and built to accommodate any of the test methods that SHRP is developing to measure fatigue, rutting, and stiffness properties of asphalt concrete mixtures. What you see here are 4 main components of the test system. There's the computer and electronics, which controls and records the data as the test is being performed. There's a hydraulic unit in the back that supplies power to the load actuators. This is the main test frame. It allows us to apply both vertical and horizontal loads. This chamber lowers down so that we can change the temperature environment around the specimen as well as apply pressure to the specimen. And the final unit on the right is what we call the environmental unit, which supplies that pressure to the specimen or changes the testing temperature. As I said before, we can apply both vertical and horizontal loads to the specimen. We can do this either independently or simultaneously. And right now we have a rubber specimen in here instead of a regular asphalt concrete specimen to show more movement so that you can actually see the actuators moving. Over here we have several different types of specimens. The equipment was designed to accommodate many different sizes and shapes of specimens to perform almost any type of testing you want to perform on asphalt concrete. Over here on the monitor we're displaying the actual loads that are being transmitted to this specimen right now. We're measuring both the vertical and the horizontal load. This computer software allows us to define any type of testing sequence that we want. We can vary the frequency, the different waveforms, magnitudes, and you can save all of that so you can call that up and repeatedly run that type of test. It records all the data and enables you to print it out in a spreadsheet type format or do graphing or anything you want pretty much.
I'm Tom Kennedy. I'm the principal investigator of the A001 contract, which is charged with providing coordination of the asphalt research program and the ultimate development of the final products. The contract is with the University of Texas. The device that is shown here is a piece of equipment that was developed as part of the asphalt program as a screening test to evaluate the compatibility of the various asphalts and aggregates that might be utilized in an asphalt mix in the United States or the North American continent. This is not a specification type test, but again is to be used to make preliminary judgments as to whether a particular source of material would be acceptable. The idea is to take the aggregates in question and place them in this column. The gradation and the sizes are approximately the same as anticipated will be used in the actual mix that's to be designed. And we then provide a solution of toluene and asphalt cement, which is circulated through this column of aggregate. The net effect is that the asphalt will be adsorbed onto or adhered to the surface of the aggregate, and we would then make a measurement to determine how much asphalt was had adhered to this aggregate in question. We then add water to the system and repeat the process, and as water passes through, this asphalt would be removed from the aggregate surface, leaving a net amount of asphalt. If a large amount of asphalt has been removed, then the material probably is not compatible and that source of aggregate might be eliminated. If we find that a large amount of the asphalt still remains, then that shows a compatibility between the two materials and provides some acceptance.
Again, this is a technique that would not necessarily be run by each and every material supplier, but only when additional information is needed prior to going into the final mix design. This is the compaction device, or type of compaction device that has been selected for the mixture design and quality control for the field. It's a gyratory compactor. This is a very old model, but a new model will be developed capable of molding specimens that are 6 inches in diameter by 6.5 inches tall, or 4 inches in diameter by 4.5 inches tall. It's relatively inexpensive, and the material that is produced, the specimens that are produced, simulate the properties of the material that come from an actual highway that has been constructed by construction rollers. The procedure basically is to place the material in the mold, which is shown right here. This mold then is placed in here, and it is lifted up at an angle, and then this table spins so that the material basically is kneaded and shoved into place. The tests that we have run to date indicate again that these materials that are produced, specimens like this, are very, very similar to the properties of the material that occur on the roadway. This will be used again for design, and will also be used in the field laboratories in the control of the mix.
I'm Jim Moulthrop of the University of Texas at Austin, and involved with the A001 contract for SHRP and the asphalt program. One of the features of the new binder specification is constructability, and it's very important in field quality control of bituminous mixtures to be able to determine the viscosity of the binder at very high temperatures, 275 degrees Fahrenheit, in that range. It's important to do that to be able to have some handle on the ability to mix the material as well as to place and compact it. This is a piece of equipment by which we can determine the elevated viscosity, or viscosity at 275, of the material in a very simple, quick, and convenient way at a reasonable price. The way this viscometer actually operates is a specimen of asphalt cement is placed into this vial. It then is placed into this temperature control device called a thermocell. And then this spindle with a conical configuration then is loaded down into the specimen, and it's allowed to rotate. And through a series of calculations that the equipment is capable of doing, the viscosity is determined. From that, then, we can determine the correct temperature to both mix, place, and compact the material, which is a very important aspect of quality control. This is, in terms of the components, this is the viscometer, this is the thermocell, or the constant temperature device, and this is the temperature controller. This happens to be one model of the machine. This is another. Both do the same thing. This is programmable and a little bit more expensive. This is less expensive, but again, I would say it will accomplish the same exact thing that we want to have. So quick, simple, easy to use in the field, very adaptable for quality control at the plant site and in the field, where it's very important to determine these characteristics of the binder. In order to be able to predict the performance of binders in the new SHRP specifications, it's important not only to understand how they perform when mixed and placed, but it's also necessary to understand how they perform with time. And we do know that binders age while they're in service. So one of the techniques in order to be able to predict performance is to be able to measure that in the laboratory. The technique that's been developed under the program to be able to do this is what's called a pressure aging vessel. Essentially, a standard thin film oven pan is loaded with asphalt cement. It is placed in a thin film oven by the standard AASHTO procedures. After that, then it is then taken in the same pan, placed in a series of shelves, and then this is merely placed into this vessel, which, like so. A lid is then attached. This is placed in a bath to control the temperature, and then this is affixed to an exterior air cylinder, and we apply a pressure using the compressed air. The times and temperatures under which this test will be run are yet to be determined or fixed as part of the specifications, but nonetheless that's the procedure. One of the important features of this is that by placing 2 pans of binder in this test method, we then generate enough material where we can run all of the required binder tests that have been shown previously. One of the other products of the SHRP Asphalt Research Project has been the development of a new and improved procedure to be able to measure the properties of asphalt recovered from pavements. Typically today we use a chlorinated solvent, and we also with the current procedures tend to age or harden the material excessively while we're recovering it from the pavement. In this process that was developed at Texas A&M University as part of the 2A contract, we have a procedure whereby the asphalt concrete specimen is placed inside of this cylinder, and a toluene ethanol solvent is then placed in with the mix. This is then rotated with this motor, and the liquid extract that's drawn out of the mixture is then placed through a filter and then into the rotovap system and evaporated off, so that the residue or the residual asphalt cement recovered from the mixture is then able to be tested again in the binder tests that have been described earlier.
The purpose of this device is to measure the viscoelastic properties of asphalt cement. And by viscoelastic we mean that the material behaves partly like a fluid and partly like a solid, which is the nature of asphalt cement. This is a sophisticated device. They've only been available at a reasonable price for 5 to 10 years. And we feel it will go a long way towards solving a lot of the problems we have in pavement. This device is in particular designed to reduce some of the problems we have in this country in rutting and shoving of pavements at high temperatures during the summer months. This is the second proposed SHRP specification test on asphalt cement. What you see behind me is the bending beam rheometer that was developed at Penn State and is now available commercially. In this test we take a small beam of asphalt which is prepared using a mold that looks like this. The beam is placed in this device in a bath which is cooled to about -15 degrees C. A load is applied up here which bends the beam, the deflection is measured, and from that we calculate the stiffness at low temperature, which is a good indicator of low temperature cracking. Low temperature cracking is a big problem in the northern U.S. and Canada, and through this test we hope to eliminate this problem from our roads.
My name is Todd Scholes. I'm with the Oregon State University, and what we have here today is the thermal stress restrained specimen test, and it is used to investigate the low temperature cracking characteristics of asphalt concrete. The system consists of an environmental cabinet with load frame and loading capabilities, data acquisition system, and computer to control the load and collect and reduce the data obtained from the test. What we do in the test is cement a specimen between platens, suspend the test specimen between the load ram and the reaction base. Then we cool the specimen by introduction of liquid nitrogen, which is controlled by a temperature controller. When we get the specimen to a set point temperature of around 3 degrees Celsius, we begin cooling the specimen at a rate of 10 degrees Celsius per hour. What that will do, when that occurs, the specimen tries to contract and we pull it back to its original length. As we cool the specimen more and more, we have to pull on the specimen harder and harder. So the general trend of the test is as the temperature cools, the load increases until eventually we get to a point where it fails. The the load on the specimen has reached its tensile strength and the specimen fails. So we take each specimen all the way to failure. And that is the basic, what we get out of the test system is load at failure as well as the temperature at failure.
What we're looking at here is a computer program which brings together everything associated with SHRP, that is the binder specification, the mixture specification, all of the tests that are being developed under SHRP, putting them together into one package to allow a user to produce a mix design for an asphalt mixture that applies to specifically the area where he's located. The computer program is set up so that the user develops inventories of materials. Raw materials are kept in aggregate and binder inventories, and then mix designs have a mix design inventory associated with them. The user can look at gradations, various gradations of aggregates that can be evaluated as part of the mix design. He can look at them on screen and determine if they are appropriate. As part of the mix design, the user will be looking at the densification of mixes, the compaction of mixtures, and so he'll be able to look at the method by which a mix design will densify. And here we have the number of gyrations in a compaction and gyratory compaction machine versus the increase in density. And so for different asphalt contents, we see that the mixtures will densify in a different way. There will be limits that will be put on and attached to the way a mixture densifies. This will help him select which mixtures are appropriate ones to do evaluation on and which mixtures are not. Once he determines which mixtures to do an evaluation on, the user will then be able to look at the various properties, air voids, voids filled with asphalt, and voids in the mineral aggregate, and how they change with different asphalt contents. The specifications, the criteria will be read out of the specifications based on environment and traffic for the project, and so the limits on which the mix has to meet come out of the specification and are displayed for the user. The user then can select an appropriate asphalt content and move on to the accelerated lab test to determine the mechanical properties of the mixture. When the mix design is done, then the user will be able to export the entire mix design onto a floppy disk that can be taken out into the field and used by the construction engineer, onto which the quality control information is added, and hence everything dealing with a mix from the beginning to the very end will be included all on one computer file.
SHRP's long-term pavement performance experiment will be the basis for the next generation of pavement design. All 50 states, all the Canadian provinces, and 10 other countries are working together in this huge experiment. I'd like to show you some of the testing equipment that we're using and one of the many byproducts of the program that you can use now.
My name is Robert Van Sandbeek. I work for Braun Intertech Pavement and with the SHRP North Central region. Today we're looking at the falling weight deflectometer, commonly referred to as an FWD. It's used for the non-destructive deflection testing. SHRP is using it to monitor the structural capacity of the pavements in their test sections. Typically, we're looking to repeat the testing on a 5-year cycle for the GPS sections. Special pavement studies, we're on a tighter schedule. The device is used to simulate rolling tire load. The way it does it, it lifts the load, drops it on a set of rubber springs. The load's transmitted to the pavement through a 12-inch diameter load plate, and there's 7 sensors that monitor the response of the pavement to that load.
One of the test procedures that was introduced in 1986 to support pavement design was resilient modulus. And this has proved to be a very, very difficult test for state highway laboratories to run, but we have come up with some procedures that will allow them to calibrate their tests and doing standard proficiency tests so that they can see how well their tests are being performed in relation to tests being done by other laboratories at other state highway agencies and commercial laboratories as well. These are synthetic samples that we use to calibrate the resilient modulus test. Each of these has a known modulus value so that a state highway agency can test their equipment to see whether or not it's reading properly. These could be used at the beginning of any test series. The Strategic Highway Research Program is truly an international activity. Including the United States, 29 nations around the world are participating in SHRP activities. Some of these activities include the provision of lone staff to the United States in the conduct of our studies so that this information can be transmitted quickly around the globe. 10 nations are currently performing long-term studies of pavement performance related to the studies that are being conducted in the United States and Canada. In this way, pavement research information gathered around the globe can be related, and the inference space of information that we have on pavement performance will be increased accordingly.
In our brief walk through this exhibit, you've seen about half of the total number of products that SHRP is developing. If you think you can use some of these products, let us know. Call us at SHRP or call one of our regional offices, or ask your state SHRP coordinator. We'll be happy to send you more information about anything you saw here. A lot of different manuals, brochures, announcements, and reports are available. Give us a call and we'll make sure you get what you need. SHRP was developed by the states to help you solve your problems. As you've seen here, there's a lot of new things coming out. Now, here's John Tabb, Chief Administrative Officer of the Mississippi Highway Department and Chairman of the SHRP Executive Committee.
The theme of the project is SHRP now because we have a great number of products that are ready to be used now. We hope that you can get your state to participate and help in the implementation of this program.